Additive friction stir deposition. It's a 3D printing technology that my buddy Mark here is going to tell me about. Hey, Mark.
Hey, how are you?
I'm great. So first of all, where are we?
So we're in Blacksburg, Virginia at Virginia Tech, but we're not on campus. We're off campus at the U Research Group Lab, where we work with additive friction stir deposition. I'm a PhD researcher under Professor Hong Yu in the Material Science and Engineering Department, and we are a part of Virginia Tech MADE, the Virginia Tech Center for Additive Manufacturing.
Friction stir deposition.
Yes.
That is a technique where a metal is, with pressure and friction, made to deposit.
Yes.
Okay. Additive means we just put layers to it, right?
Yes.
Okay, and this is what this machine can do.
Yes, it is.
Tell me a little bit about that process.
Okay, so additive friction stir deposition is a solid state metal additive manufacturing process. So majority of additive manufacturing processes involve melting the material. In this process, we never melt it. So we only take it up to about 80% of the melt temperature, and we reach the flow stress state of the material where we're continually plastically deforming it. So we're very closely related to forging.
Metal additive, we can use electricity or heat, and we melt it. Lasers hit powder to form it, and that's just typically how it's done. This is a solid state process.
So we take a solid half-inch by half-inch bar of material. Absolutely. Readily available. We order from McMaster Car. You can find it anywhere.
It's just
it's just a generic bar of material.
And we have
very, very little restrictions when it comes to feed material. So as long as it'll fit in our feed channel, we can run it through, which gives us a lot of different unique opportunities, which we'll talk about later.
Yeah.
We have a tool. It's basically a cylinder that's running in the machine, and it has a square channel in it that will key into this bar of material and will feed material through. Underneath the tool, we're holding it at a large pressure, and we're rotating, imparting shear deformation. And that shear deformation is what promotes the flow of material and is going to break down any oxides and help metallurgically bond that material with prior layers. So this isn't going to be a laminated structure. It's actually fully dense, fully metallurgically bonded, effectively generating a billet part.
Okay, when we talk about like lasers hitting powder,
yes,
there is a porosity that we have to worry about. A highly porous metal additive part can't be qualified for like aircrafts or whatever, right? You're fully dense and you're not melting it.
Yes, absolutely. So just like you would take, say, a cast component and then go through a forging process or a hot rolling process to refine all of those defects, get rid of that porosity, and improve the material structure, we have that structure straight off the printer.
And you utilize this tool head.
Yes.
And you said it's key. Because this is spinning.
Yeah, so it's spinning and it's transmitting.
You can't have a circular rod in there.
Correct.
You need it's keyed because it's. That makes a lot of sense. So you're imparting pressure.
Yes.
And in part with the pressure and the spinning, you're getting temperature.
Yes. So we don't actually input energy in the way that you would with, say, a laser process or a welding process where you're directly using electrical energy or other electromagnetic energy to melt that material or to deform that material. We're purely mechanical. So think of if you take a paper clip and you bend it back and forth, it gets hot. We're doing the same thing here. So the deformation of the material is what's actually generating the temperature and is maintaining that elevated temperature.
Wait a minute. So, okay, because I've done that. I've bent a paperclip over and over, not to the point of breaking, but enough to where I can reform it, and then it kind of stays in that state.
Yes.
That's this?
Yes, just on a much larger scale.
And this is the machine.
Yeah.
And so this is huge, first of all.
Yeah, so it's a big CNC machine, but what's different than a typical CNC is rather than having a normal small spindle motor, we have a giant spindle motor to be able to transmit a large amount of torque, and we have this big linear actuator that's providing the downforce required. So during this process, our general approximation is we have a F-150 pickup truck at the end of that tool head. So we can impart up to about 7,000 pounds of downforce from that actuator. And when we're rotating the tool to maintain deposition, especially at high deposition rates, we can get up to about 350 pound-feet of torque at the print head. So really, really large numbers.
Can we see it go?
Yeah, absolutely. All right, so right now we're just starting up the G-code. We're going to be Zing down the layer height. You can see our position up here. Once the spindle kicks on, you'll have the torque output, the speed it's spinning at. You can also see the temperature of the tool itself. And down here you have from the actuator, the speed that it's moving, and the force downward continuing that process. So as we Z down into the material, we'll hit layer height and we'll start feeding. And then we're going to be waiting there to keep building heat and start flowing material. And once material flows, we'll tell the machine to start moving. We've reached enough load to start to compressively deform that material and it start to effectively fail. But once you have enough temperature, then it can flow continuously. So rather than breaking off small little pieces, it's moving almost like a liquid.
All right. All
But
right.
it's solid the whole time.
But solid the whole time.
And that's yield.
Oh, and that's yield right there.
Normally around 330 C on the readout is when we'll start to see the material start to flow. So that's looking pretty good. I'll tell the machine to move. We're now forcing material downward at 7 inches per minute and traveling at 10 inches per minute traverse.
I see it going. Look at that.
So the temperature should remain fairly stable as well as the torque. So right now we're sitting at about 140 foot-pounds of torque and 1,700 pounds of downforce.
That's way less torque than I thought we would need.
So it's relatively low depending on the material. This is 6061 aluminum, which has a relatively low flow stress. If we were working with a high-strength aluminum alloy like 7075 or 7050, we'll see a much higher torque and higher force.
So then you just sit here and wait.
Yeah, so that's the one beauty of this is once you have it G-coded, you have everything programmed nicely, you don't have to worry about things going wrong, you just hit the go button and let it happen. There's a lot of development that goes into this, a lot of research that we've done to better understand the process and be able to do things as effectively as we do. And so once we get to the end, the print head will pick up and move out of the way, and that's your layer deposit.
And then you've got a fully dense VT logo.
VT logo.
The piece is done. Mark, you're holding it lovingly. This is the VT logo.
It's the VT logo.
Heck yeah, can I hold it?
Absolutely.
Okay. So in looking at this, obviously what you're making is something that is a near net shape, right?
Yes.
Okay. But there are advantages to that because it's less wasteful.
Yes.
Right?
Anytime you're manufacturing something from the ground up, whether it be a casting or a forging, you're still going to have to come through and machine your final features. So critical features are going to need to be machined. So this is a near net shape process, and because we have really, really good material properties, very similar to a forging, this is what we're kind of in the market for, is working in high performance applications where material properties are really valuable. And in those applications, you're always going to need post machining. So
always,
we're really
like
not
always, right?
Yeah, so we're not really changing anything in the workflow of how you would go through the manufacturing process.
Oh yeah, because in other additive processes, you're still creating net near shapes and you're having to machine them to a final spec, but it's just you're making this size part really fast.
So our feature size is very, very large. So our print volume is about 38 millimeters wide and 2 millimeters thick. So we're volumetrically depositing massive amounts of material. And although it is near net shape compared to other near net shape processes, we have a little bit more edge flash or material that needs to be removed. It all kind of decreases how big of an impact that is with scale. So our big thing is scale. This is a small AFSD
Yeah, this is
part.
small. Okay, what's the largest machine
so
that you know of?
The Army has a machine that has a print bed volume of 30 feet by 20 feet by 12 feet using the same technology. So massive print scale.
That's a room.
Yeah.
Okay. Well, I got goals, I guess. Here, I'll let you take that back. Because there's other things that we have to talk about. In talking with a net near shape and being milled to a final spec, I can see that here. But there's also smart metal. Is that right?
Yes, smart metal.
Smart metal. Like this blows my mind. And so tell me a little bit about what's going on here.
So what we're doing is we are embedding electronic sensors into metal components. And because we can 3D print solid, really strong metal that's metallurgically bonded with really high, very good properties, we can put electronics and components and then print over the top of that and effectively restore any sort of decrease in performance that they would have from machining that pocket into it using this technology.
Okay, so if we talk about how they would do it before, you could either place the sensor on
the
top,
surface,
right, on the surface, or you could drill in,
put it inside.
Okay.
Now you have a defect.
Right.
And so we can remove that defect. And so we're fully enclosing those sensors in the part. We're protecting them. We can get better information closer to an area of interest.
This is Star Trek level stuff.
Yeah. So what we'll do is we'll take some sort of same material enclosure that's going to cover up over the top of the material. machine a equal kind of pocket in the material, put that over our electronics, so it'll be flush with the top, and we can print over the top of it, and that's going to metallurgically bond this puck with that part to minimize that defect. And you can do this with a part that was completely made with AFSD. You can take a prior forging or a prior casting, machine a pocket into it, or have that as an original feature, put in a puck, and then print over the top of it. So you don't need it to be an AFSD part. You can take an off-the-shelf existing component that you're already producing and then use this just for the sensor embedding process.
Okay, this is really cool because I see some stuff here, and now we can talk about materials, because what we've shown so far is aluminum.
Yeah.
Okay, but aluminum is not the end-all be-all of what you're able to do.
No, not at all.
Okay.
So we can work with a wide variety of materials. So effectively, if it's ductile, we can print it. If you have the force and torque, you can print it. And one of the big requirements is just tooling. So what we were just running with aluminum is steel tooling. But if you want to deposit steel, all of a sudden your tool becomes a consumable. So you're required to use a higher temperature material. Typically, it's a lanthanated tungsten.
Oh, okay.
And so with that high temperature tooling, that opens up the door to a wide variety of materials. So steels, nickel alloys, a lot of titanium. We've printed copper. I know nickel aluminum bronze has been printed. So a very wide variety of materials.
You just have to make sure that your tool melts at a higher temperature
than the material that you're trying to deposit. Yeah. And with this being a solid state process, there are a lot of materials that don't lend themselves well to melt-based processing. So we work a lot with 7075 or other 7000 series aluminums that have a high copper content, so they hot crack. So you need a lot of different additives in your powder to be able to try to print them using other AM techniques. But we can print it off the shelf in the exact alloy as it was intended.
Oh, so you actually get a more pure part.
Yes.
Purity in metals isn't necessarily something, like for being able to qualify a part, that's good because you have fully dense, nice, pure materials. But like if I look at stuff like this looks like scrap.
It is scrap. So that's one really, really cool thing about this process is because it's all based on shear deformation, we have a really high feedstock tolerance. So that's about 80% dense. And so that is made of these. So this is twitch. This
scrap!
Is automotive scrap. So whether it be cast parts, stamped sheet, this has pieces of circuit boards in it.
That was a plug somewhere.
Yeah, so basically, if you mill that up to a small enough size, you press it into the general square shape of a feed bar, throw that up in the machine, and you get back to a fully dense part.
So this is an 80% dense part, and you're saying it still makes a 100% dense part.
Yes, so with that shear deformation and consolidation, think of, again, forging. So we're doing the same thing, but taking a bunch of scrap aluminum that might be cast down and really not have the greatest composition or performance, and we're upcycling it into a fully 100% dense component. And with some testing, we've seen in the 60% range of the mechanical performance of forged 6061 T6.
That's ridiculous.
That's just as printed. So might not be the best performance in the world, but it's better than what it otherwise would be, and we don't have to melt it. So because we're just throwing it straight in the printer, we're very, very energy efficient as well.
Mark, what's your history?
Kind of my foray into playing with electronics was when the FPV drone craze hit.
Really?
And I built up a drone. I taught myself how to solder and put together my own quadcopter. So that was really, really cool. And from there, I've always liked working with my hands, building things. Got out to tech, studied engineering, had a great time. And it was my junior year of college. I took a dual listed, so it was a graduate level class. And they presented some things of, this is as far as we understand this. This is what we know. This is the knowledge threshold. And I thought that was the coolest thing. And I was like, I don't want to stop. I've had a great education, but I want to keep going. And I really enjoy being on the forefront of technology. And I've always seen this need of, we're at a point where it's not what we can design, it's how can we actually make these designs? And so I saw a huge, huge need for further studying the additive manufacturing technologies, and was lucky enough to find a research group here at Virginia Tech with a relatively new process that's very, very unique. So I've been lucky enough to stay here with my education. I love it here, but the technology itself is really, really cool, because we're able to do something like this where it's not yeah, we can make this with other means, but we can do it better or in different ways and have unique outcomes that you wouldn't get with other manufacturing.
All right, there are a couple things that are really excellent right here that you're going to have to take me through, because harkening back to the smart metal that we were talking about,
Yeah.
this is smart metal. What is this?
So this is a aileron lift bracket. So this is an actual component that would be on an airplane. We got a CAD file for it. We shaped it out, wrote the G code, printed it using Afsd, and then went through that process of milling in slots and embedded sensors. So there's an array of temperature and strain-based sensors in this component. In this jig, we can load the part. We have a relatively high, medium, and low strain region of the component, so that way we can see if the strains that we're measuring are what we would expect, and you can also get an effective temperature distribution. So if you take a finite element model of how that part would behave in practice, and you know your strain at multiple points, now all of a sudden you know the strain or the stress history of this component alongside the thermal history. So if you have a part in use in practice, now that's an alternative to inspection, or hey, there was this high load event, maybe we should check out this component.
That's so cool.
Awesome.
The final example of smart metal is an aluminum video game controller. Mark, go. So in this are the sensors that we talked about, and it's got just a little, an accelerometer in there?
Yeah, it's an accelerometer. And with that, you map that out to movement, you can play some fun games. And actually, it performs quite well. And it's a very satisfying weight to play with. But yeah, there's a lot of really cool things that you can do with this.
Mark, there's no buttons on the controller, though.
Yeah, so like we were talking about with the structural health monitoring of if I have a bunch of things on the surface of my component, they might not be ideal. And if I'm going to be running a bunch of wires in a machined component, then I might as well just have a plastic controller. But in this case, it is fully embedded for maximum strength. Absolutely.
Sure, I can try. Oh, it's a really neat use case of kind of what you guys are trying to show off. Now, you're not going to make mass-produced controller bodies.
No.
But it's really cool that you can do this. Like, this is smart metal.
The fact that it exists is just very, very cool.
Mark, this has been an absolute joy learning about this, because it's not just a really neat way of doing additive manufacturing. The way you go about it is different than what's available now, and it makes lead times less for parts, and you don't put as much stress in the metals because you're not heating them, and everything is a homogeneous piece. It's all metallurgically the same. Like, this is incredible.
I'm really excited to be on the forefront of continuing to develop this process to make it more available, more easily usable, better understand the material that we're working with.
A lot of people are going to be really curious to know more about it. So look in the camera right there and tell everybody where they can go to find out more.
Yeah, so you can find out kind of our group's publications and what we do at UGroup MSE. It's a Virginia Tech domain, I believe. Just look up additive friction stir deposition on Google Scholar and see what other people are working with and see the state of the art of the technology.
Thanks for watching. If you made it this far, you're awesome. Don't forget to hug each other more. Fight for a cause you believe in. Follow your friggin' dreams. This is incredible. And as always, high five. Going? Oh, it echoed. Jump is not mapped to emotion yet. Am I correct?
Correct.
I'm glad you're still alive.